Hi. So just let me know when we have to start the session. Take it.
Okay. You can start.
Great. So let me just put up a quick recap what we have done in the morning batch. In the morning one, we had a discussion about the SCF convergence calculations. Along with the SCF convergence calculations, we discussed about the band gap calculations. After the band gap calculations, we discussed about.
Please share with me. Please share. Yes, we can see.
Great. So, a quick summary what we have discussed till now in the morning session. We had a discussion about the SCF convergence calculations. After the SCF convergence calculations, we discussed about the band gap calculations directly from the SCF itself. And then we discussed about the magnetic property calculation. And now I'll switch on to the structural optimization, which is the most time-consuming calculations in the quantum physics or quantum chemistry, you can say. And then I'll take all of you toward the structural designing part. In terms of structural designing, we'll start with the nanosphere, the monolayers, pi layers, and then I'll take all of you toward the E versus K diagram calculation, or you can see the fine structure calculation. And then finally, a glimpse of what exactly is the molecular dynamics and how to use it for the estimation of intermolecular interactions or maybe some kind of diffusion study. Okay.
So your sound is not right. Sound is very low.
1 minute. One. Now am I audible?
Yes. Now you can hear.
Everything I know myself. One.
You can rejoin the meeting if you are facing the issue.
But to guide the screen should show something. Everything wrong. Do one thing. Can you like that?
Google Meet. सत्ताजी स्वतः आप बघितली. Still not getting clear on.
Now the voice is clear and screen visible.
Yes. Now.
So now let me start. Actually, I did one modification over here. So now what basically we are going to do it, we are going to start with a new calculation, which is the structural optimization calculation. Now, what is the structural optimization? Why do we have to do it? What kind of results software is going to yield? There are things we need to discuss. So, same silicon lattice I am taking and I am making some modification in the structure. As in, I just remove the two oppositively arranged base-centered silicon atom with the phosphorus. You can substitute any other element of your choice with the element of your choice. Now, the question arises that why do we have to do the optimization? See, previously we were taking the unit cell structure of the silicon. That structure was experimentally derived using the X-ray crystallography. So, which means the atoms they were already present in their stable structural form. Stable structural form as the atoms were experiencing balanced interatomic forces of attraction and the repulsion, and the net residue force on each and every atom they were equal to zero. So that is why we call the structure as a stable structure. But now, after the substitution of the silicon with the phosphorus atom, we had disturbed the bond length, the bond angle, plus we had added two extra electrons to the system that will cause the interelectronic repulsion. Again, size incompatibility as compared to the previous one, silicon being a bigger size, phosphorus a smaller size. So, because of these changes, charge as well as the size incompatibility, the unit cell will no longer remain same as compared to the initial silicon lattice. It may expand, it may shrink, or it may not overall expand or shrink. So that is what we have to do, the structural optimization. That is the logic of doing the structural optimization. Now, how to carry out? So under the cell, nothing much is there. Under the element, again the first thing, you need to take the ultra soft pseudopotentials. And then under the atom, I had made the changes. Under the HCF, now, a precaution. So I have seen that few of the researchers, while carrying out the structural optimization, they take the cutoff values. This is incorrect. Why is it so? Because note it down, unless and until you already have the optimized structure, you cannot do the SCF convergence calculation to obtain the cutoff values. So since this structure is already non-optimized, non-stable, I cannot do the SCF convergence cycle to obtain the cutoff values. And unless and until I have the cutoff values, I cannot keep it over here. So conclusion, for the structural optimization, please keep any combination of your choice over here. Once you obtain the stable optimized structure, you can do the SCF convergence cycle later on to obtain the cutoff values. So ideally, the first calculation is the structural optimization. If the structure is not optimized, not pre-stabilized, then the SCF convergence calculation. So what I'm basically doing, I am keeping a value of, let us say, 20, and then I'll take 5 times this time. There is no hard and fast rule that we will have to take the 4 times or the 5 times of this previous one. It should be in between the 1:4 to 1:12 ratio. Now, afterward, now why the very low values? Because note down, the calculation time depend on the following values. The higher the value you take over here, the calculation time will definitely increase. And that increase will not be 1 minute, 2 minutes, that will increase exponentially. So under the total charge, I am defining a -2 this time. Why? Because we have added 2 extra phosphorus. We have added 2 extra electron to the system. So accordingly, -2 charge will come over here. Similar thing lies over here, K points. I have seen some researchers writing that they have taken the cutoff values of the Kx, Ky, Kz. It cannot be unless the structure is not optimized. How can you take the cutoff values? So keep some random combination over here and then take the smearing as like the Fermi-Dirac. So although there is a one more parameter over here under the convergence threshold, I think I should discuss this part because in the morning there was a difficulty in understanding how to optimize the bigger system. So participants note down, there is a condition line over here as the threshold. Threshold corresponds to something under Rydberg unit. Rydberg defines the energy unit. So note down, by default, what software tries to do? It tries to minimize the energy of the system till the energy change becomes less than -6 in the successive iteration. Sir, we haven't got anything. Wait a minute, I'll make it clarify. This is rather required for a bigger systems. See, this is the graph we had already seen in the morning session, that you got the overall energy of the system like this one. But how we have arrived at this energy? What software does? Software iteratively do the calculation with a given combination DF which we have specified, it sees that initial energy decrease. This will be somewhere around, say this is 351 and this is 359. So almost a change of 0.008 unit. You can say 8 into 10 raised to the power minus 3. From here to here, it will be around 360 to around 361. Again, a change of 10 raised to the power minus 3. Then it reaches at this stage. At this stage, the energy difference is very clear. That means at this stage, software says that even though I am trying to take the next combination, I am not able to reduce the energy value further. Now, why at this particular stage? Because we are keeping a default condition of delta E equal to minus 6. That is the energy change equal to 10 raised to the power minus 6. Now, what we can do it for the bigger molecule, having lot many number of atoms compared to this one, we can always relax down this condition. Relaxing down this condition, what does it mean? Please try to understand it. See, default is minus 6. If I change this value to minus 5, now I am giving an instruction to the quantum espresso that you don't have to reach up to 0.000001. Rather, the moment the energy difference becomes equal to 0.40 please stop the calculation. This reduces the calculation time, but again, there is a compromise with the accuracy also. And this is what I said at the beginning of the today's lecture, that the more the accuracy you want, the more the time you will have to give. But it doesn't mean that you will devote unlimited amount of time to do the calculation. So therefore, always you can reduce down this value. Now, the lowest value which you will find in the literature report, people go with the 10 raised to the power minus 3 also. I repeat, the lowest acceptable value of this delta E, which you will often find in the manuscript, it is 10 raised to the power minus 3 unit also, which means 10 raised to the power minus 6, most accurate, minus 3 accuracy compromises. Please do not ever directly take minus 3 if your laptop system supports calculation within a day, then take minus 6. If within a day your calculation won't converge, then only you reduce it to minus 5, minus 4, minus 3. That's it. So, in a summary, I changed the charge part over here, and under the electronic optimization, I had not changed anything because I don't know how much time this particular sample will take. Then I'll move on to the next panel. The next panel is the optimization panel. So participant, note down, using the quantum espresso, you can do all kind of SCF calculation, optimization, molecular dynamics, density of states, band structure, Nose-Last event calculation. That is useful for the chemical reaction studies, the transition state structures, intermediate structure, activation energies, the time-dependent density function theory for all kind of new visible spectroscopic analysis for non-calculation. But Burai at this stage, it is limited to only these options which are listed below. That means using the Burai, you will be able to carry out these fundamental calculations. But if you want to go with these options, the more advanced one, you need to manually incorporate the code in the input file. Like the way we have done in the today morning session for the bandgap calculation directly from the SCF, we gave the input command by ourselves as in NPND equal to 32. So I'll come back to the optimize. Under the optimize, there are various options. Restart mode, I'll not use it out. Max time, it is just the empirical value. And then there is an option of a variable cell. Now let's understand what is the meaning of the variable cell. See, variable cell optimization, which is often written as VC relax optimization in the manuscript, gives the instruction to the software that during the optimization, you have the liberty to either increase the unit cell volume or decrease the unit cell volume. Like in the present case, out of 18 silicon atoms, we had substituted 2 of them. So out of 18 silicon atoms, we had substituted 2 of them. That means close to, I can say, 10% of the substitution. That will definitely break the change in the unit cell parameter. And that is why the variable cell optimization become more meaningful. On the other hand, variable cell optimization, that you have to click over here. On the other hand, if you have more than 100 number of atoms, and wherein you are making there won't be much change in the unit cell volume practically, And in that case, you can reduce the computational time by carrying out the non-variable cell optimization. So these are the two available options in the quantum espresso. I have seen researchers always going with the variable cell optimization by considering that it is a more accurate model compared to the non-variable cell. But you need to know when you need to carry out the variable cell and when you don't have to carry out the non-variable cell. That is a take-home message. If the structure is too big, substitution percentage very less, then variable cell is meaningless. Rather directly go with the variable cell because that will reduce the calculation time enormously. There is although one more parameter over here named as a threshold. This is defined as the delta F condition. What is the meaning of the delta F condition? See, please note down these parameters because they play a crucial role in reducing the calculation time. So, as like I said, in case of balanced structures, all these atoms they experience balanced forces, and if the forces are balanced, the net remaining residual force on each and every atom become close to zero. So that is what is the value line over here. We are giving the instruction to the software that during the energy minimization, structural optimization, please keep delta F equal to less than 0.001, which means software has a limit, a lower limit, that it has to reduce the residual forces till it becomes less than 0.001 on each and every individual atom. Now, for a bigger system, having a lot many number of atoms, very small structural substitution, you can always change this value to -2 also. Achha, one more thing, you have to keep a unit as EV per angstrom. In manuscripts, you will find EV per angstrom more often used as compared to Rydberg unit. So this value can definitely change from -3 to -2 because at -2, now you are giving a liberty to the software that do not decrease the residual forces up to 0.001. Rather, if the residual forces are only 0.01, stop the calculation there itself. Again, there will be a compromise with the accuracy, but not significant one. So that is I'm leaving it to all of you. Or otherwise, what you can do one more thing. So these are the couple of the research articles I'll share with the team so that you can have an access to it. You can see that people have modeled the properties of the tin monochalcogenide is the monolayer bilayer by making use of the well-known quantum espresso software package. Therein they had used the delta F condition of their monolayer structural optimization was carried out using only 4 atoms per unit cell. How we will have a detailed discussion when I'll discuss about the designing part. Where is the delta F condition? It is lying over here. So they have taken a delta F value of only 0.01 EV per angstrom. And this is the most standard value majority of the researchers they prefer to take. This is the supporting information of a JPC letter. People have investigated the property of hydrogen storage as in the lithium temperated boron sulfide monolayer. The structural optimization delta F value of a 0.01 EV per angstrom. Okay, so I hope now this point is clear. So keeping this value as 0. I'll go with the -3 first. If the calculation won't converge within few seconds, few minutes, I'll then reduce it to -2. And I'll do the variable cell calculation because definitely there will be a change in the unit cell volume. 0.001 EV per angstrom. Again, you can also carry out the pressure dependent studies that if you are working on some external pressure, you can define the pressure over here. 3 lines and simply go to the run icon and to execute the calculation. The participant note down, the optimization calculations are the most time consuming calculations, whether you are using the Gaussian, quantum espresso, material studio or whatsoever. So wait, it can take around 10 to 15 minutes. Meanwhile, I'll show you the results of some of the previous calculations so that we can save up the time. So over here we have what we have done. We had optimized the structure of AU nanocluster unit all the way from 1 atomic unit to up to 14 atomic unit. Why up to 14 atomic unit? I'll discuss it out. How the optimization basically gives the result, I'll discuss using these examples. So I'll open this AU9 because there was a significant change in that structure. So to optimize the AU nanocluster unit of AU9 atoms, so how we came up to this particular part, I'll discuss after 15 minutes. I'll show you the result of optimization on it. So see, this is the initial structure. We took it on a completely random basis for the optimization. And as the optimization proceeded, the software first changed the interatomic distances, found some stable bond between them, progressively changed the intermolecular angles, and finally it converts to this structure like a bucket kind of a structure. So that's how the AU9 nanocluster unit look like. Pretty simple one, and it does not take much time. As far as I remember, these optimization, it barely took a one single day for all the 14 structures. We can always give it a check. Yeah, so it took only 3 hours to compute to stabilize the AU9 cluster unit. Similarly, there are a couple of more nano cluster units which you can always see. AU13. So this is the initial structure which we took, and on optimization, see, this is what you can see on optimization. Software is changing the distances, the shape, and finally the structure took a shape like a crown shape. Still the calculation going on. And all these calculations were done at a quantum mechanical DFT model. And likewise, we have all the results. I'll share the results with all of you so that you can have a quick look at the Burai interface. I'll consider the silicon phosphorus optimization result if the calculation is over. It is still running. The optimizations are the time-consuming calculation. Meanwhile, what I'll do, I'll move on to the next part, which is the designing of these kind of structures as the nanostructures. Regarding the structural optimization, I discussed the substitutions, the delta E and the delta F condition. Delta E acceptable up to -3, delta F acceptable up to -2. Correct. And then as and when the optimization will be done, I'll discuss the result part of it. Now, how to design these kind of nanospheres, the monolayers, and some of the heterostructures. I'll discuss it next, maybe next 20 to 30 minutes. And then we'll be back on to the band structure along with the MD studies. So basically, we use a software named as Avesta. Again, it's an open access software to carry out the designing part of these nanostructures. I'll first discuss how to design the nanospheres. To design the nanosphere, you basically need a unit cell structure of the gold as a zip file. Zip file you can easily obtain from the materials project I discussed in the today morning session. After you get the zip, what next you have to do? So let me see if I have this zip, otherwise I'll download it. I'll better take it to the mute folder first. So that's how the unit cell structure of the gold look like. It is in the cubic lattice. So what next we have to do it to design the gold nanosphere. Let us fix an objective to design the gold nanosphere of 1 nanometer. To design, so you can design up to 2 nanometer also, but beyond 2 nanometer, I won't recommend because generally after 1.2 nanometer or 1.5 nanometer, these kind of quantum confinement effect, they generally die off. So better that you confine the nanoparticle, nanostructure designing, nanosphere designing up to max 2 nanometer. Experimentally, you may be working with the bigger samples, but note down those bigger nanospheres. They are not show. They does not show a periodic arrangement of the atom throughout the unit, throughout the nanosphere. Rather, you have the discrete nanocrystalline unit within the lattice. So, therefore, conclusion: even though practically you may be working with a 100 nanometer, 200 nanometer nanoparticle, theoretically you have to model up to 2 or 1.2 nanometer only. That is the maximum limit you have to take. for the DFT calculation. Now, how to design the nanosphere out of this cube? The step number one, edit data, unit cell. I basically need to enlarge this unit cell because the present edge length is around 0.4 angstrom. So with 0.4 angstrom, I cannot design nano sphere of 1 nanometer. So first go to the transform option and I'll increase the present volume of the unit cell such that it can accommodate few more number of atoms. So now you have got a supercell out of that small unit cell. I can maximize for a better clear picture. So this is the supercell of the gold nanocube, you can say. Now I want to extract the sphere. To extract the sphere, there are some simple steps. First, export the data as in the VSP file format. Why is it so? Again, there is a discussion, but I would like to avoid for a time being AU pass Cartesian coordinates, and then simply drag the AU vast in the Vesta interface. The next step after that, after opening the AU as a vast file, add a dummy atom at the center of the box. Why? It will become clear. Wait for a minute. Structural parameter. So dummy atom, I'm keeping, let us say, cesium. I'll keep some label to it. And at the center of the box, the coordinates are going to be the coordinates of the centroid, as in 0.5, 0.5, 0.5. Apply and OK. So we have added a dummy atom at the center of a box. Now, why are we calling it as a dummy atom? Because this is not the part of a system I would like to model. So I just added it for some reference so that I can construct a nanosphere. Now, next step, go to the edit option, go to the bonds option. And under the bonds option, we have to click onto the new search atom bonded to A1, keep the A1 identity as cesium. Why is it so? Understand it. Because we are giving the instruction to the software to locate all the atom bonded to A1. And A1 is our cesium atom. Over here, to draw the nanosphere or to construct the nanosphere of 1 nanometer, I'm going to give a value 5. Understand why is it so? See, when we are defining this value as 5, it stands for 5 angstrom. It means I am giving an instruction to the software to locate all the atoms coming in a proximity of dummy atom at a distance of 5 angstrom. Why 5 angstrom? Because if I look 5 angstrom from here, there, it will construct a nanosphere of 1 nanometer. 0.5 is the radius. Diameter will become 1 nanometer. Click onto the apply. And as you click onto the apply, you are able to see that software has located all the atoms coming in a proximity of 0.5 nanometer with respect to the dummy atom. In the next step, you just have to delete all the non-bonded atoms. To do so, there is a select icon over here, this white color arrow. Make a selection. Here at this step, our maximum participants, they make some mistake. They somehow in a little bit hurry, and then they erase those atoms which are either bonded or they keep those atoms which are unbonded. So please note down, if you are going to do the same mistake, the stoichiometry will rather get disturbed. So please don't make those kind of mistakes. So I'll make a rotation and check, have I deleted all the unbonded atoms or still some are there? Still some are there. You just have to drag and select the atoms which are unbonded and use the delete key of your keyboard. I'm done. Let me check by rotating it that all the unbonded atoms, they must be removed. Correct. So all of them are rather removed. So now I don't require this dummy atom anymore because I have already located all the atoms coming within a nanosphere of 1 nanometer. So finally I'll delete this dummy atom. And I'm done. I can erase these bonds, otherwise it is not required because I will remove it by itself. So that's how the nanosphere of 1 nanometer can be easily constructed. You can see it in a better form so that it will look like a spherical shape, like this one. And similarly, you can see the polyhedra model, which gives you even better picture. So we are done with the designing of the nanosphere of gold 1 nanometer. Next thing, see, in Burai, only two types of file formats are allowed: the SIF and the XYZ. Bars, it is not allowed. So what we are going to do it, we are going to finally save this structure as an XYZ, and then we'll take it to the Burai. So do so, file, export data. Name it as, because there are a couple of same files in the laptop. Second one, save. And please don't be in a hurry that you click onto the yes. It says that do you want to save the hidden atom as in those atoms which we had erased. So if you are going to save the hidden atoms, it will rather save the structure as in the nanocubical form. I don't want the nanocubical form, I rather want the nanosphere. So click on the no icon, and that's how you can get the XYZ file. Now simply take this file to the SIF folder which we created in the morning session. C drive SIF, drop it over there, and then you can navigate to the My Computer option, SIF, locate the structure which you had constructed. So that's how a gold nanosphere of 1 nanometer look like. Pretty simple one to design it. What you can always do, you can add the unit cell periphery so that the structure looks little better. So these are the customization you can always do to see the structure in a better form. You can play with the atom color, the edge length, the bonds and all. So this is the gold nanosphere of 1 nanometer in size. And similarly, you can design n more number of structures. Now, participant, at this stage, I would like to discuss one more thing, that regarding the neutral nanospheres and the charged nanosphere. So if I look at the atom column, under the atom column, the software says that 1 nanometer nanosphere of gold, it consists of almost 38 atoms, and all of them are neutral. As against, I'll show you one more structure. So this is a nanosphere of same 1 nanometer, but it is of CDS, cadmium sulfide. Cadmium sulfide, 1 nanometer nanosphere, it has got the atomic arrangement like this one. Same approach we had used. First, get the SIF, enlarge the unit cell, add the dummy atom, locate the atom, erase unbonded atom, and then keep the file in the XYZ. Now, in this structure, there is a one important thing you have to observe: the atom list. In the atom list, there are 11 number of cadmium atom and the 9 number of sulfide atom. So each cadmium atom has got a charge of +2, and each sulfide has got a charge of -2. So similarly, now if I talk about the charge on this nanosphere, 11 cadmium, 9 sulfide, a total of 2 excess cadmium with a charge of +2 are there. So that means this overall nanosphere will get a charge of +4, and that can be easily validated using the zeta potential measurement. Experimentally, you can also validate it out that the units that this nanosphere will get a charge of +4. In the morning batch, there was a question by one participant that, sir, how to know that whether the doping which we have done is it the correct one or not? So to answer that question and correlate that question over here, what you can do it always after the doping, if experimentally you are designing it, go for the XRD measurement. XRD measurements do the ritual refinement that will give you the exact atomic position if you have the access to the XRD instrument. Otherwise, you will have to play with this atom. Similarly, if you are working with the charged nanosphere, what you can do it practically, you design, you synthesize, go with the zeta potential measurement and see what is the charge. After that, if let us say the zeta potential measurement says that this particular nanosphere, which your experiment is synthesized, has got a charge of plus, I am just assuming of some value, got a charge of, let us say, +2. That means this structure will not be the good choice. You have to either reduce the number of atoms, increase the size. You have to play somehow with this structure so that the experimental charge and the number of cadmium sulfide ion, they will balance out with each other. So there are a couple of experimental approaches you can always use in conjunction to validate your computational studies. So that complete the designing of the ionic nanocrystal also. Next, fine. Let me see if the results calculation of silicon phosphorus is over or not. It's over. So I'll show you the result over there. I hope the designing of the nanospheres with these two examples must be little clear to all. I know we are going little fast, but I need to maintain the speed so that I can elaborate what quantum espresso can do in detail as a fundamental calculation. Otherwise, there are more advanced calculations. So this is the result you are visualizing of optimization.movie. I'll click over here. See, the result right now at this stage, the software says that the initial structure which we started from which we started, it was like this one. What is the please observe. I'll click onto the animation key and see what you observe. I'll again click. I'll click last. Great. So now what this animation says that the initial structure of silicon doped with the phosphorus which you took it had some edge length, it had some bond distances, but since phosphorus is smaller in size compared to silicon, two extra electron inter-electronic repulsion unit cells should expand. So accordingly, you are seeing that the second structure, what exactly is the second structure? Software has done the forces calculation, the residual forces calculation, and it found that the residual force is still greater than the magnitude of 0.001 eV per extra. And that is why it again did the force calculation, again residual force calculation, force being a vector quantity, it changed the atomic position in that direction and again found the next structure as a structure number 3. Again, it found the residual force is greater than 0.001 and successively to minimize the residual force, it ended up to the 11th structure wherein the residual force is at less than 0.001 eV per extra. Now, this structure you have to take for all subsequent studies, whether the SDF convergence to estimate the cutoff value, the band gap, magnetic study, or whatsoever. And how to take this structure to the new window? Simply, you have an option over here. You can click on the new project. That will enable you to select the folder wherein you can save the optimized structure, give some name to it. Give some name to it. That's all. So you have got the optimized structure of the silicon dope with the two phosphorus atom. You can see the changes in the edge length. So previously, without the substitution, the edge length was around 5 point, as far as I remember, it was around 5.46, correct, angstrom unit, and now it has increased to 6.053 unit. Similarly, the atomic positions have also changed. So simple, easy to do optimization. Now, coming back to the few more results in the optimization panel, because each and every result will go to your manuscript, there is a graph, optimization.tne. This graph simply indicates that how the energy of the system change with each and every structure. Structure number 1, which we had mentioned, it has got this much energy in the Rydberg unit. Second structure, less residual forces, energy decrease. Eventually, the residual forces decrease to a limit of -3. The delta E become less than -6, and the software converts the structure at the 10th or the 11th level. Then same thing you can see for the lattice parameter. The lattice parameter along the A direction or the edge length along the A direction increase. It eventually becomes saturated. Similarly, along the P, all these graph will go to your manuscript. And along the C also. So since it's a cubic lattice, the expansion occurred uniformly along all the three directions. If in case you will be working on the hexagonal lattice, for hexagonal lattice along the C, there will be a major expansion. Along A and B, there won't be much expansion or shrink, you can say. So that's all about the optimization, correct? And now I'll back onto the Vesta interface. In the Vesta interface, next I'll take all of you towards the designing of the monolayers. So monolayer has a one problem that it has got huge number of atoms, literally huge number of atoms. I'll just show you one thing. I'm just doing one modification and I'll show you what exactly we have to discuss. So participant, on my screen, there is something. What exactly is that and how to design? We'll discuss. Right now, I would like to show you one thing so that the calculation become meaningful. Initialize model. Uh, I don't know whether this is visible or not. Is this graphene sheet visible to all the participants? A tiny graphene layer. Just too tiny, and I don't know how to zoom in the view. Is it visible?
Yes, sir. We can see.
Great. So see, this is a graphene structure. This is the graphene structure, and it has got almost, I can say, more than 500 number of atoms. Studying the 500 number of atoms using the DFT model, it is next to impossible task, and that too in the solid state material devices. So therefore, there is an easier and a newer approach that if you want to mimic the property of these kind of monolayers, which shows periodic arrangement of the atom, instead of taking the entire atomic arrangement in the layered form, you simply take its unit cell. You simply take its unit cell and study its property. As that, so till now, what we were doing, we were investigating the property of the silicon material. Silicon material, if I practically talk about its dimension, will be in the micrometer, millimeter, or maybe the centimeter also. But those many number of atoms, if I start to take at the DFT model, I won't be able to do it. So therefore, to replicate the properties of those macroscopic material, we just took a unit cell structure of their material in a three-dimensional form. Similarly, to study the properties of these elongated materials as the two dimension, one dimension, you don't have to take the entire structure for the property estimation. You just have to design the unit cell and study their property. Now, some of you may have a doubt that, sir, is it acceptable in the literature? So to answer that question, what you can do, you can always have a look. I'll share this folder with all of you so that you can have a look onto this research article. This is a relatively newer approach. I think starting from 2015 onwards only, people are using this approach because DFT calculation results, they definitely overpasses the result of the typical classical mechanical studies. So you can have a look in this research article. People have investigated the behavior of the tin monochalcogenides monolayers. This is the tin selenide, the upper one. This is the tin sulfide, the lower one. Now, what you can do it, you have a choice that you take the entire atomic arrangement, atomic atom arrangement, and study the property. But that way, the DFT calculation in the quantum espresso, it will never ever complete. And that is what is the trouble majority of the researchers they face. They say that, sir, I am trying to optimize the structure. This is the first calculation we have to do it. I failed. It is running from last 13 days. I definitely say that never ever run any calculation which lasts for 13 days. Please wait for at least a day. If within a one day the calculation won't converge, you have the ways to reduce the calculation time. So what they have done, they have taken a simple unit cell structure of this layer, which comprises of only 4 number of atom per unit cell to study the entire property of this design material, starting from their optical behavior, their dielectric constant, the band structure, and the density of states. Simple theoretical calculation only. If we look at this research article, there are no experimental studies in it, only theoretical studies, and that's all. Similarly, all the research articles which we have over here, all of them uses the concept of unit cell of the monolayer. Now, how to practically design them, I'll discuss that part. In the West. So I'll take an example of graphene only. Otherwise, we can take an example of molybdenum disulfide also. The vanadium disulfide also. So basically, you will have to start with their zip file. The monolayer of the graphite is the graphene. So I'll start with the graphite. This is I'm going to design the graphene unit cell. Graphene unit cell. So keep the SIF, open the SIF in the West tab. The step number 1 is to directly save the structure as a mask. See, each and every step has a reason also, but I'll not go into that because that will take a lot of time. Save the structure as directly as a vast Cartesian coordinate. Drag the vast file. Next, align the unit cells so that you see the longest axis upward. Otherwise, see, I am going to take a lattice plane which is the XY plane. Otherwise, you have the option to select the lattice plane of your choice. As that, if you want to extract the atom along 100 lattice plane, define the lattice plane over here. You can see this is the 100 plane. Similarly, if you want to go with the 110 plane, define the 110 plane. And now you can see all the atom coming within the 110 plane. Similarly, if you want the 111, the diagonal one, so that's how the lattice plane, the 111 look like. So whichever lattice plane you would like to study for the monolayer structure, you can select that lattice plane and keep it horizontal, and rest of the structure you have to keep it vertical. So I am keeping the XY plane horizontal and rest of the structure I am keeping it vertical. Now at this stage, the structure looks like a tri-layer system. I don't want to design the tri-layer system or the multiple layer system. My objective is to design the monolayer. So what I'll do as a first step, I'll erase the two top layers. I am done. And now, see, my objective is not to design the monolayer. My objective is to define the unit cell of a monolayer. So, in the next step, I need to align the unit cell horizontally like this way. And I need to erase all the atoms which are outside the unit cell periphery. So, I can see 1, 2, 3, 4, 5, 6, 7, 8 atoms are there which are completely outside the unit cell periphery. I'll erase it off. I am done. And now for the last step, I need to erase all the atoms which is touching the upper x-axis and this y-axis. So over here, I don't have any atom, but yes, definitely I have an atom over here. I'll erase it off. And now I am done. I'll save the structure and take it to the bureau. As an XYZ file only. This is going to the graphic. The date is 2nd of March. You want to save the hidden atoms? Definitely no. I'll take that file to the bureau. In the bureau, there is a final modification which we have to do it. I'll discuss it out. Correct. And now in the bureau, I'll see the structure. So this is I designed graphing too much here. So under the modular option, let me change the background because I don't like the gray background. I'll add that. So that's how the structure at this stage look like. But there's a trouble at this stage. See, if at this stage I will use the elongation or I create the supercell, what will happen? The trouble will be there is an extra vacuum zone in between the individual molecular unit. So therefore, at this stage, I will not consider the structure as the unit cell of the graphene because on periodic arrangement, it will not generate the structure of a graphene. What I'll do, I'll reduce the extra vacuum zone along the x-axis, along the y-axis, and I am done. So let me check whether this individual unit will act like a molecular unit cell of a given graphene or not. Initialize model. Scaling, I can keep any scaling the XY direction. Previously, I did 10, 10, 1, and now I'm doing 6, 6, 1. Now I hope this will be visible. So that's how you can easily define the unit cell of a monolayer. You can even further enlarge. It is not like 6, 6, 1. You can take any random combination of your choice because of the periodic structure. That's what. So that simple unit cell simplifies the calculation. So, for the monolayer structure. Now, participant, there is a one more thing we need to discuss regarding this monolayer. So this is the structure of the monolayer of a graphene, of a graphite. I'll show you one more thing that on translation of the structure along the z-axis. Why so will discuss. I can see that there is another unit of the graphene lying over here. Why is it so? Yes. So this is because of the periodic nature of the zip files. Zip files are the symmetrical file. So what you can see over here that the two individual graphene layer, they are separated by a distance equal to C edge length. This is the X edge length. And at this stage, this is equal to 10 angstrom. So note down, whenever you are going to work with a monolayer structure, you need to keep us a vacuum zone in between the two isolated layers. Why is it so? Because if you won't do it, the structure will rather belongs to the pi layer. Why is it so? Please understand. At an intermolecular distance of 10 angstrom, I cannot think of any kind of predominant forces of attraction. Van der Waal, London dispersive forces, ionic forces, metallic bonding. So therefore, if there is no intermolecular attraction in between these two layers, the system will behave like a monolayer. And this vacuum zone in literature, if you see, people generally look for the 15 angstrom. I never ever recommend to go up to 15 angstrom because even if you take 10 angstrom, 12 angstrom, 15 angstrom, the results are going to be same. 15 angstrom, it only increases the calculation time. This article, if you see 15 angstrom, I have seen people taking up to 20 angstrom also. 20 angstrom, if you want to take, you can take it, but that way the calculation time will exponentially increase. See, they are taking a vacuum zone of 20 angstrom. 20 angstrom intermolecular interaction, I don't know which force will exist at 20 angstrom, which they are trying to minimize. So I hope now the designing of the monolayer unit cell, the vacuum zone must be clear to all. One last thing which I'll show is how to optimize these unit cell of the monolayer. Modeler. So we had this graphene XYZ, correct? I decrease the distance. Now what we need to do is, since it's a new system, the forces are unbalanced. You need to balance it out by the structural optimization. And for the structural optimization, same steps you have to adopt. 3 lines, pick the ultra soft model. Atoms, now you can see only 4 atoms are there. The 3 lines, STF. Now again, I cannot keep the cutoff values because the structure is still not optimized. K points, I'll not keep it right now. After the optimization, I'll do the convergence over here. And then under electronic optimization, I'll first go with the -6. If it won't work, then I'll reduce down this value and finally optimize. Now, participant, at this stage, you need to remember one more thing, that there are two types of optimization, variable cell and the non-variable cell. If I will go with the non-variable cell optimization of this structure, it will become Herculean task. Why is it so? If I'll go with the variable cell optimization of this structure, it will become a very difficult task. Why? Because software will try to reduce this vacuum zone, will try to bring the intermolecular distance as lower as it can be to maximize the van der Waal interaction. And that way, the structure will no longer remain the monolayer. It will rather converge to the multiple layer. So therefore, you are bound to do the non-variable cell calculation of these kind of monolayer structure. So I'll go with the -3 only. And there are a couple of more entry cases we have to see, but time won't permit me. I can see already 1 hour session is gone. Calculate run, and the calculation will not take much time. Let's draw new folder. Meanwhile, this calculation will go on. I'll discuss about the heterostructure part. This is graphene, and then we'll move on to the electronic structure as in band structure calculation. So let it go on. We'll see the result after a few minutes. I'll quickly jump on to the Vesta interface and see how to design the heterostructures. And for the heterostructure, I'll take an example of 360 on a fullerene. Similarly, you can design the core shell nanoparticles and nanowires. I'll take an example of 360 onto the graphene, a simple system like this one. 360 on a graphene. So you have got all these examples over again. You have got the two-dimensional layer of a 360 polar graphene, and onto that you have a 360 unit. So how to design them and how to decrease and find the optimal distance. Let's do it. And to do so, I'll start with the graphite SIP only. I'll close this interface and I'll reopen otherwise. I will remove the problem. So, in the Vesta, I'll require a file corresponding to C60. I already have it over here, C60.zip. And then we have a file corresponding to, but before that, let me extract out the individual coordinate unit out of this. Edit data events, transform. Same thing as like we have done it for the gold nanosphere. Since coloring three-dimensional structure to so there are a lot of coordinates in the system. I don't require these many. So I'll want only one. But before that, let me export the structure as a mask. Otherwise, being a symmetrical system, it will give me the problem. So C60.pass. Save location. Three lines C60.pass. See, once you learn these calculations, they are like just I am doing it pretty fast. C60.pass. Where did I say? I think we have what the C60.pass. So there are so many C60, I don't want these many, so I'll just extract out one. Then we will design the graphite graphene layer, and then we will finally merge them. That will complete the heterostructure designing. So you can design all the way the composite materials also, but composite material has a little difficult task because if they are not periodic, that means if the atomic arrangements are not periodic, then using the DFT model become a very time consuming task, and majority of time you won't get the result as well. So better that if you are working on the periodic structures, then only you try the quantum espresso because it defaults to the periodic DFT calculations. So now this is the individual coordinate. I am done. I'll just save it out. Save. And now that graphite is also there. Where is it? Just large it because I want to have the one. Okay. This. Now this is a tri-layer. I don't want the tri-layer, so I'll first save it as a mask. Extra only I'll save. Start is almost going to get mask stage. Coordinates. Okay. I'll open the graphite mask. We need the tri-layers, so I'll erase off the two top layers. And I'll save the structure as an XYZ file first. Export data. Extract, graphite, 3 lines, XYZ. This will no longer be a graphite. This is graphene. I'm done with the saving of it. And now, how to take these two structure in a single window? Pretty easy task. Open the notepad. open the XYZ file corresponding to both of them. Yeah, so you can see that in the C60.xyz, the atomic position for 60 atoms are written. For graphene, 134 atoms are written. Simply take all the atomic coordinates of one species to the second structural file. You can do vice versa also, that is the your choice. And finally make the change in the first value. This file has got 60 plus, this was 134, right? 194 number of atoms are there. And now you can open this file back into the Vesture and you will be able to see both the structure in a single interface. You modified C60.xyz, right? So now you can see that you have got both C60 and the graphene on top of each other. Next thing what you can do, you can play with the intermolecular distances by changing the XYZ coordinates in the Excel sheet. So that's what I'll not move on to it. I'll just leave it on to that. One more thing I can discuss because there is a little bit of a more time is there. You can always functionalize these layers in the Avogadro platform. And then you can take the structure to the DFT model as the Avogadro. Again, it's a free software. Graphene.xyz. I hope it will open because pretty big structure. It will open, will take a little time, but it will definitely open. It's a one body problem. So this is the graphene structure in a West. Avogadro, you are saying, let us say you want to functionalize this structure according to your choice. You have the option lying over here. Let us say if you want to put up the amine functionality, so you can put up, if you want to put up the carboxylic acid functionality, so you have the ways to design, select the atom, make the connection according to your choices. Control set, adjust hydrogen, yes. And then you have oxygen. So right now I am not concerned about the bond distances, bond length, and the bond angle because we are going to optimize it. So this is the COH. I can turn a double bond. Now this is the unbalanced structure because bond length, bond angle, you can see they are the disturbed one. So before you take this structure for the quantum mechanical structural optimization, I strongly recommend that you at least optimize it using molecular mechanical model because that way you will be able to bring some accuracy and more accuracy the DFT will give you. How to do the molecular mechanical optimization? Click onto the E, click onto the chart, and now you can see that the energy of the system decreases, although it says positive value because it is a molecular mechanical model. Otherwise, the energy cannot be the positive value, but it is progressively decreasing and stabilizing the structure. And this structure you can take it to the Vestra, Burai, wherever you want to take it. So I hope the functionalization must be clear. I'll just save it out and let's see how it look like in the Burai. Graphene.xyz 1604. So there are huge capabilities if you want to perform using the free software. In morning batch, I showed that till now almost like we have trained 4,000 participants on these DFT calculation using the quantum espresso. And till date, as per the data, 159 researchers have already published a meaningful article on those calculations which they have learned fundamentally. So, graphene.xyz, I have to say, right? Is the graphene.xyz. So that's how it looks like. You can simply functionalize, pre-stabilize, pre-optimize, and then you can take the structure for the subsequent studies. As simple as that. Now, I'll jump from the designing part. We have designed the nanospheres. I'll briefly summarize nanospheres of 1 nanometer. We saw the cadmium sulfide 1 nanometer, the concept of a charge. Then we designed the monolayer, the unit cell. Then we saw the functionalization in the Avogadro. I'll now quickly take all of you toward the band structure calculations and then the molecular dynamic part. But why is this right over here? We have discussed that, right? So now I'm on to the electronic structure as in the band structure calculation. For the band structure calculation, I'll again take the help of the lookups because morning we had studied it a little bit. 3 lines. And to do the band structure calculation under element, same pseudo potential you have to keep at which you have done the FTF convergence calculation. Atom, I'm not bringing any change. SCF. Now, note that for properties calculations, as in the electron hole mobility, conductivity, photovoltaic behavior, you need to keep the cutoff values here. You cannot take any random combination. 6, 6, 6, bearing type, Fermi-Dirac model, nothing under the magnetization, silicon non-magnetic in nature. The 3 lines. Optimization, I don't have to do it because the structure is already optimized. I'll directly jump onto the band structure calculation. And under the band structure calculation, you have to specify the K points there, whether it's the gamma K and all. I'll not enter into that part. I'll give you the link how to get these K point path for a given type of a crystal lattice. Give me a minute. K point. So what you can do, you can easily go to the Wikipedia, and you will find that for each and every type of unit cell, there is a specific set of K points that you have to put up in the Burai interface to compute their band structure. Right now, I am just going with the software default. They are also good, but it is always better that you configure by yourself. Then I'll click onto the run icon, correct, save project, extract, and this is the folder first. So, sure. And now it will not take more than a 2 minute. So that's all. After the band structure calculation, I'll discuss out about some molecular dynamics calculation. Molecular dynamics calculation generally it defaults to the classical mechanical model because generally people prefer the molecular dynamics calculation when the atoms in a system they are too huge. The number are too huge, maybe approaching around 1,000, 2,000, or even greater than that. But we can always do the molecular dynamics calculation on our periodic structures. Periodic structure as the meanwhile the calculation is on, I'll discuss it out. Absorption behavior. Absorption. So see, there are a couple of research articles wherein the people have used the molecular dynamics studies using the quantum espresso to investigate the intermolecular interactions. As in this research article, people have studied the interaction of the phenol, carcinogenic molecule. I guess I'm not an organic chemist, so as far as I know, it is a carcinogenic in nature. How it interacts with the undoped graphene layer and with the doped graphene layer. So what they have done, they have designed the system and as against taking them in the bulk form, because in the bulk form you can only go with the molecular dynamic studies and the results does not matches with the experimental values. Rather, they prefer to take the isolated units to do the DFT calculation because result accuracies are very high. So what basically they have done, they have taken the graphene layer, they have taken the crystalline graphene layer and then they have substituted with respect to the different elements. Boron, I think they have highlighted boron, aluminium, and the gallium. And then they took the phenol, the different orientations onto it. And then they investigated the molecular dynamic studies and obtained the interatomic interaction energies. Now, how to do these studies? That is what I am going to highlight. You can see that they have taken the completely horizontal arrangement, the vertical arrangement, the lateral arrangement. They had tuned the intermolecular distances and study the energy graph and obtain the best possible distance for the maximum interaction, all at the DFT model only. Similarly, next article talks about the same thing, JPCC, wherein these people have taken the graphene, then they had absorption of the amine-based substituent they had taken in presence of a defect and some adsorbent. Same studies, they had taken the PB quantum espresso They had used the quantum espresso calculation, the DFT model, and then they substituted the atom at the respective position. They took the molecules, and finally they had evaluated the absorption energies. And then finally on the absorbed structures, the band structure analysis, the density of states analysis, and so on. So purely computational studies. And like that, you have huge number of articles. I just kept few of them onto the drive. And now how to carry out these calculations using the MD, I'll discuss it out. So for that, I'll make use of the results which I already have it with me. So let me look at it like this way. Say this recently used option, you can explore all the calculations which you have done in a single interface. Let's end it. So participant, meanwhile, the band structure calculations are on. I'll discuss about this MD studies. So you can see what we have done. We took a graphene layer and then onto that we took a hydrogen molecule. What we wanted to study how the hydrogen molecule get absorbed onto this graphene layer. And to do so, I just took a random intermolecular distance between the graphene layer and the hydrogen. Why only one particular hydrogen? Because that will give you more accurate result employing the DFT calculation. Otherwise, if you will take the Avogadro number of molecules, you are bound to perform the classical mechanical calculation, which limits the accuracy of the result. Now, under the atom, you can see one thing that right now I am keeping the intermolecular distance between the graphene and the hydrogen as approximately 1.4 angstrom, the difference between the two Z coordinates. So 1.4 angstrom, I cannot think about any kind of intermolecular attraction. Rather, we are in the repulsive zone. Lagrange or potential graphs you would have seen. So at this stage, 1.4 angstrom, we are in the repulsive domain. So what we basically did, we went to the STF option, calibrated the options over here with the cutoff values. And then after that, we went to the MD option. And in the MD option, as like in the morning session, Professor Prashant has highlighted that how many steps you have to carry out, how many steps you have to take, what is the time steps you want to give, that you have to configure. So for this study, I took a time step of around 200 seconds. Like I took a time step of around 200, and each step I define it as a 1 femtosecond. Why is it so? Because I already did one particular calculation and I saw that the calculation got converged within 7 femtosecond. 7 femtosecond doesn't mean the calculation time, it is the time within which the interaction got converged. If I talk about the calculation time, this MD study, I think it took around 6 to 7 hours on my laptop machine itself. So that is the initial setup we did. And again, you can do the temperature control part because these kind of adsorption, deadsorption, they depend on the temperature. So if you want to do the calculation at the control temperature, you can always select this option and define the temperature. Similarly, if you want to do these kind of molecular dynamic studies, you can define the pressure condition also. That is up to your choice. What would you like to prefer it? Now I'll talk about the result of it. In terms of result, couple of files are there. I'll discuss this MD movie only. And what about that graph? Where is the graph of MD in a total on this one? So please have a look. This is the result of MD ENE molecular dynamics. What it's depict. Please have a look. I'll play from beginning. See, this is the initial structure which we took it for the MD studies. At 1.4 angstrom, I was a little skeptical that there will be an intermolecular repulsion. And when the calculation started, the results were hydrogen molecule was going far from the graphene layer so as to minimize the repulsion, maximize the attraction, and finally it reaches up to this distance to maximize the attraction and minimize the repulsion. At this particular distance, I can see the distance is going to be around 3.6 angstrom. And 3.6 angstrom is a pretty good value for the intermolecular van der Waals interaction. So that's why you can easily carry out the MD studies regarding the time part. As you can see that each time step corresponds to around 0.0005 picosecond. Roughly, I can say 5 femtosecond is 0.5 femtosecond. So if each time step corresponds to 0.5 femtosecond, I can say that within 35 steps, the software converts the structure. That means it took around almost 17.5 femtosecond for this hydrogen molecule absorption onto the graphene. Now, some of our previous participants, they had a doubt that, sir, is it an absorption or is it a deabsorption? Participant, note down, this is the absorption because we are seeing the hydrogen molecule going far from the graphene because our initial model was incorrect. If I would have taken this hydrogen molecule greater than distance of 3.5, it would be coming toward the graphene layer because the final distance will remain same. This is the optimized structure. And this optimized structure, again, you can take it to the view sheet for all kinds of subsequent studies. One last thing I'll show over here, that is the MDENU total graph. So this is what you can see, that as the number of step increases, the time increases, the energy of the system decreases, and then you reaches to the equilibration stage. So equilibration stage define that now you have reached to the global energy minima, the energy minima beyond which there are the thermal vibrations. And I hope all of you would have seen those atomic vibration in the hydrogen molecule. Please see, because the time scale we are keeping femtosecond. So within femtosecond, we can definitely see the higher frequency stretching. So that is what you have observed over here. And accordingly, when the two atoms were going far from each other, energy increases. Coming closer to each other, energy decreases. So that's what the behavior you are seeing. Although there are a couple of more graphs we have to see, but time limits. I'll now move on to the silicon band structure, which is the last part. It's still on. I hope some have previous result. I'll discuss it on to that. Give me a minute. Meanwhile, one more thing, because in the morning batch, there was a confusion regarding the availability of the supercomputer and the accessibility of these paid software. What you can do is that if you're also having a trouble at CRA, I discussed about the online platform wherein you can run these calculations for some minimal charges. These are not our charges and neither I am promoting it. Since my research scholar, they are using it. So that is what I am highlighting it. On this platform, you can carry out the calculation of the quantum espresso. They had pre-installed it. Fast, lamps, Chromax, and many more softwares are there. I think I can discuss about their, I can show you about the pricing part. They are relatively inexpensive, I would say. You just have to design the calculation software is already there, submit your input file, and then the calculation will run. So pricing and all, it's here. So I won't recommend to go through the free one because the data won't be private here then. For your own manuscript, you need to do your private calculation. So you can see that almost like $100 per year. $100 per year, how much it will be around? It will become 10,000 at the present USD cost of 100. So 10,000 per year, I don't think so. It's a very expensive part. Otherwise, if you want to go for the enterprise, that means more number of account members, you can get it in the bulk. So that depends up to your choice. What would you like to do it? I'll close it down now and I'll move on to the band structure calculation. It is over now. So let's see the sum result. The project is not saved. Do you want to save? No, I want to do it. Let me see what was the changes. No changes. Calculation over and now it has turned to green. So calculating, it's over. So participant, in terms of band structure, have a look. The band structure of the diagram, it look like this one. Let me make some modifications so that we can have some meaningful discussion. 3 lines. Now see, in this graph, you have got couple of valence bands, you got couple of conduction band, but I am not interested in all these conduction band and all this valence band because majority of the properties I get it from the highest energy valence band and the lowest energy conduction band. And I can see that this is lying over here. So what I can do, I can zoom in the graph from -1 to +1. And I can put up a scale bar of maybe 0.2. A little too small. It's fine. So what you can see that this is the enlarged band structure diagram of a silicon cubical lattice. I am highlighting cubical lattice because the moment you will change it to hexagonal and another one, this diagram will change. Now, what this diagram depict, the first thing which I usually infer from it, whether the material corresponds to indirect band gap material or direct band gap material. So since I can see that the lowest energy point on the conduction band, highest energy point on the valence band, they are at different K point. Their angular momentum components are going to be different. And accordingly, I can classify the material as an indirect band gap material, which will not be photoluminescent active material. The transition probabilities are going to be very less. And accordingly, I won't be able to use this material for all kind of photovoltaic active material. If I want to design some photoluminescent active material, my material should be the direct band gap material. Similarly, if I want to design the material for photovoltaic application, it should be the direct band gap material. So this material will not be good for both photoluminescence active material and as well as the photovoltaic material. Now, how to read the band gap? We need to locate the lowest on the conduction band. This value around 0. I can say 32, and then the highest on the valence band. This value will be around minus 0.28. So the gap between these 2 points comes out to be 0.6 EV, and that perfectly matches with the band gap we computed in the morning session, 0.6 even maybe at the cutoff value. So therefore, the band structure, either you use the band structure calculation or you use the STF calculation, the values will remain same. Now, although you can infer about the electron mobility, hole mobility, effective masses from the curvature of these valence band and the conduction band, but I'll not enter into that. I can see only 8 more minutes are left. So that's all about the band structure, which I need to discuss. So with that, I am done for what I need to discuss in terms of Burai. I just put up the quick summary because almost like 3 hours is gone. So 1 minute. Again, am I audible? Because again, this Gmeet is hanged. Am I audible?
Yes, sir, you are audible. Hello.
It's fine. It has come. So I'll just put up a quick summary. We started with the fundamental of what we can do using the quantum espresso. We started with the SDF convergence calculation, and using the SDF convergence cycle, we minimize the energy of the system by by increasing the cutoff values. Then we discussed about the band gap calculation for the silicon cubical lattice. We discussed for the some part of the ionic crystal also, that for the ionic crystal you have to remove the charges. Some organic molecule, that molecular unit is still there. Transitional can confirm that the entire molecular unit is there. And then we discussed about the magnetic properties, the magnetic moment per atom site, the different positions. And then we had a discussion about the structural optimization as in VC relaxed, non-VC relaxed. Then we